Welcome to Natural Deduction Part 10. In this video, we're going to look at doing natural deduction proofs in order to prove a logical truth as our conclusion. A logical truth is a statement that is necessarily true. So if you did a truth table for a logical truth, it would be true on every line of the truth table. Here's a natural language example of that. If either you like ping pong or you like Quidditch, and you don't like ping pong, then you do like Quidditch. So we can actually prove logical truths with a natural deduction proof using the conditional proof and or the indirect proof rules. And it will vary from case to case which rule we can use. So let's take that example of the logical truth we just saw. You'll notice on the first line of this proof in our example, it begins not with the premise, but just with the conclusion after the slash. A logical truth is always true, so it does not require any premises or any additional assumptions to prove. So it looks different from all the natural deduction proof problems we've done before. The problem is presented as a conclusion after a slash, and that's it. And so you want to look at the form of the conclusion, the logical form, to figure out if you want to use conditional proof or indirect proof. In this case, the form of this proposition is a horseshoe. It's a conditional. The horseshoe is the main operator. So we can use conditional proof. That's the rule that lets us prove a horseshoe from starting from nowhere, just an assumption. So we indent our assumption on line 1. We're going to assume the antecedent of the conditional we want to prove, as per usual with the conditional proof rule. In this case, that's parentheses p wedge q close parentheses dot tilde p. And then we want to look at our assumption and strategize how we can derive the consequent of the conditional we're trying to prove just from that one assumption. So you'll notice if we simplify out the two conjuncts, p wedge q and tilde p, we can use those together with disjunctive syllogism to prove q on line 4. And that's what we want for our conditional proof. On line 5, we exit out of the scope of our assumption and we create this new conditional that has as its antecedent our original assumption from line 1, and as the consequent of the conditional, what we were able to prove with that on line 4. And as usual with conditional proof, the justification on line 5 will be lines 1 to 4, all the indented lines with the conditional proof or CP rule. Let's do some examples of proving logical truths using both the conditional proof or the indirect proof rule. So in this problem, we have as our conclusion a conditional. So that implies we're probably going to want to use the conditional proof rule. If we're using the conditional proof rule on this problem, what should we assume? We're always going to assume the antecedent of the conditional we want to prove, which in this case is Q. So we're trying to use this assumption to prove that entire consequence. Parentheses Q horseshoe R, close parentheses horseshoe R. And you might be wondering, how can we get all of that compound proposition, out of the simple proposition Q? Can you see a way? The answer is we have to make another assumption. And this is something you can do as many times as you want with the conditional proof and the indirect proof rules. There's no limit to the number of times you can use them in one proof. However, each time you make an additional assumption, you will have to exit out of the scope of each assumption separately, using either the conditional proof or the indirect proof rule. And that's why we indent further on line 2 to show this is a second assumption that has its own even narrower scope than line 1. So if you look at what we're trying to do, we're trying to prove the entire consequent, parentheses Q horseshoe R, close parentheses horseshoe R, in order to complete our first conditional proof with assuming Q. We're trying to prove the whole consequent of the main conclusion of our argument. However, the consequent we're trying to prove is itself a conditional. So why not use conditional proof again to this time assume the antecedent Q horseshoe R, which is the antecedent of the consequent we're trying to derive from our initial assumption Q. And now that we have this second assumption, what can we do with it? The goal is to prove the consequent of that second conditional, and that's going to be R. So how can we do that? Well, we can use modus ponens with lines 1 and 2 to prove R. So now that we've proven R, which is the consequent of the second conditional we're trying to prove, what's the next step? We want to exit out of the scope of our second assumption, creating the conditional parentheses Q horseshoe R, which was our original assumption, horseshoe R, which was what we're able to derive from that original assumption. However, we're not done with the proof yet because line 4 does not match the main conclusion we're supposed to have. And also, we have not exited out of the scope of our original assumption. We have to get completely out of the scope of all of our assumptions whenever we prove a logical truth. So what's the next step of this proof? Now we're ready to finish. We can see that the assumption Q led to the further assumption parentheses Q horseshoe R close parentheses horseshoe R, and that matches the form of the main conditional we're trying to prove after the slash at the top. So we can exit out of our first assumption straight away, creating a new conditional, this time with Q as our antecedent and all of line 4 as the consequent. And notice the justifications overlap. So the justification for line 4 is 2 to 3 conditional proof. That was the second set of indented lines. But because line 4 is itself part of the scope of the assumption on line 1, we're going to include line 4 when we justify line 5. We use all of lines 1 and 4 with conditional proof to prove our main conclusion on line 5. Let's look at another example. This one also has a conditional or horseshoe as the main operator. So which rule should we use with this? We're going to use conditional proof, make an assumption that's identical to the antecedent of the conditional we want to prove. And now the goal, as with every conditional proof, is to try to derive the consequent of our desired conditional from our assumption. So as a first step, let's simplify out the two conjuncts from line 1. And this will set us up for using a rule that will allow us to get our consequent that we desire for our conditional proof. When we use simplification on line 1 to derive the two conjuncts, then we see those conjuncts p wedge q and tilde p do fit another logical rule, and that is disjunctive syllogism. If we use disjunctive syllogism on lines 2 and 3, we can derive Q, which is exactly the consequent we want to have for this proof. So now we can exit out of the scope of our original assumption, and the proof is done. We've created this new longer conditional using our entire initial assumption as the antecedent and the simple proposition Q, which was our final implication of that assumption, as our consequent. Let's look at another example. This one is a negation, a negated compound proposition. So which rule are we probably going to use with this proof? If you see you're trying to prove a negation, it's good to try an indirect proof assumption. In this case, we're assuming the logical opposite of the intended conclusion. And if you interpret indirect proof as allowing you to assume the logical opposite of what you're trying to prove, not just the negation of it, then you can just drop that tilde. Otherwise, you could also assume a double negation of the conclusion. And either way, you'd be able to use rules to generate a contradiction. So let's look at line 1. We need to strategize. How can we generate a contradiction from this assumption? Well, perhaps you can already see how we're going to do this if you can think a couple steps ahead. If you were stuck, it's not a bad first step to simplify out the compound propositions from your conjunction to see if you can work with them. Especially with these logical truths, your initial assumptions will often be rather large compound propositions, oftentimes with a conjunction operator that allows you to simplify them out and then work. Once you have the conjuncts on separate lines, you can use other rules on them. So on line 3, we will also simplify the second conjunct. Now, can you think of any ways using lines 2 and 3 to generate a contradiction? Well, perhaps you're not there yet, But notice that if we use implication on line 2, we can create a disjunction where the disjuncts are identical. And that's going to be the key move that helps us generate a contradiction. Can you see what rule we can use on line 4 to get us closer to generating a contradiction? If we use tautology on line 4, we can get rid of one of the tilde s's. And then look at lines 3 and 5. Do you see the contradiction? If we use modus ponens on lines 3 and 5, we can get s, and there we have it, tilde s on line 5 and just s on line 6. So the indirect proof rule requires us to generate a conjunction of the contradictory propositions on the last line of our indirect proof before we discharge our assumption. Now that we have that contradiction on line 7, we can discharge the assumption and conclude the negation of our original assumption, which is identical to the main conclusion of this argument. Let's look at another practice problem. This one is simple, but kind of deceptively so. You have to think through the nature of our rules sort of carefully to figure out how to derive this. The logical truth is tilde p horseshoe tilde p, or if not p, then not p. So it is a conditional, so what should we assume with this proof? We want to assume the antecedent tilde p using our conditional proof rule. And then the goal of this is to generate the consequent of our conditional. But in this case, the consequent of the conditional is also tilde p. So what do? What's the next step? The next step is actually the last step. Because in this case, the antecedent and the consequent happen to be identical, as soon as we make our assumption on line 1, we've already also derived our consequent of the conditional on line 1. So we exit out on line 2 and we create this new conditional, tilde p horseshoe tilde p. And in this case, we're using the conditional proof rule as a justification of line 2, but there was only one line in the scope of our assumption, so we just cite line 1. Let's look at another sample problem. This one is a disjunction, and the first disjunct is negated. Now, you can prove disjunctions using one of our assumption rules, indirect proof or conditional proof. Do you remember which one it is? The answer is conditional proof, because the horseshoe or the conditional can be translated into a wedge. You can use the implication rule to go back and forth between them. So always remember that if you are trying to do a proof where you make an assumption, you can use conditional proof rule to also prove wedges. You just have to use another material implication step at the end to turn it into the disjunction or wedge that you need. The other thing to remember is that when you use implication on a horseshoe or conditional, the first disjunct of the disjunction you create is going to gain a negation. So when you make your initial assumption for a conditional, you want to drop that negation, or in some cases add a negation from to your initial assumption using conditional proof. So in this case, all we need to assume is R and not R dot tilde R. We're dropping the negation from the first disjunct in our conclusion because we know we're going to add that negation again once we use implication. And then the next thing to remember is that we're trying to at first create the conditional proposition using conditional proof. So the negation of our first disjunct, or the logical opposite of our first disjunct, is going to be our antecedent of that conditional. We're going to use that antecedent to try to prove the consequent, which is the second disjunct. So in other words, we're trying to prove tilde parentheses s wedge tilde s close parentheses. But you'll notice s does not appear anywhere in our initial assumption, R and not R. So how can we generate this whole other compound proposition in the second disjunct involving s? Well, the key thing to realize is that from a contradiction like R and not R, you can prove anything. So in order to do this, you start out by simplifying the two conjuncts if the contradiction is listed as a conjunction of contradictory propositions. So we're going to use simplification twice on lines 1, deriving R on line 2 and tilde R on line 3. And then we have to think, how can we prove tilde parentheses S wedge tilde S close parentheses from R and not R? The answer is by using addition to add the entire proposition we want to prove after a wedge. And then we can use the other contradictory proposition, in this case tilde R, with our disjunction created by addition to derive that proposition that we want. The rule we use is disjunctive syllogism with lines 3 and 4. And yes, this technique can be used with any contradictory set of propositions, if they're both lines in your proof, to create any other proposition you want. So that basically is showing how, logically speaking, contradictions allow you to prove anything, and that's why they're logically problematic. Okay, so the goal of this was to prove our second disjunct from our main conclusion up above as the consequent of our initial assumption. And we've done that. Line 5 is identical to the second disjunct from our main conclusion. So what's the next step? We're going to exit out of the scope of the assumption from line 1 and create a conditional statement or horseshoe, using our initial assumption as the antecedent and what we ended up with on the last line of our conditional proof, line 5, as the consequent. And now, because this line 6, the proposition, has a horseshoe as an operator, we have to do one final step to convert it into a wedge as would match our conclusion. And as you'll recall, we use implication on line 6 to do that. And you'll see our antecedent from line 6 has gained a tilde or negation on line 7 to match the form of the material implication rule. Another example. This time we're trying to prove a conditional. So what rule should we use for our assumption? The answer is conditional proof. We're going to assume the entire antecedent of that conditional in our conclusion as the assumption. And now what are we trying to prove with this assumption? We're trying to prove the consequent of the main conditional tilde L or not L. So you want to look at your assumption on line 1 and figure out how you can use those propositions to prove not L. As before, it can be helpful to simplify out a conjunction in order to make use of the separate conjuncts with other logical rules. So we're going to use simplification 2 times on line 1, once on line 2 to derive the first conjunct, second time on line 3 to derive the second conjunct. Now, can you think of any rules you could use with lines 2 and 3 to help you prove not L? If you use De Morgan's on line 2, this will help set you up for proving not L. If you were not able to see how this would help you, notice that line 2 is a negated conjunction, and that's very distinctive of De Morgan's. Now, it is not the case that whenever you see a negative conjunction, you're going to want to use De Morgan's, but it's something to think about and try out if you're ever stuck in a proof. So now, can you think of how we can use lines 3 and 4 to generate tilde L? Well, first off, it's close to matching the form of disjunctive syllogism, lines 3 and 4. However, it doesn't quite work because tilde M or not M is not the negation of the second disjunct on line 4, because the second disjunct on line 4 is tilde M. So we're going to have to use the double negation rule before we can use lines 3 and 4 to prove tilde L. We could either add 2 tildes to line 3, thus making it the negation of not M, or we can remove 2 tildes from the second disjunct on line 4, which is what I've chosen to do here. So now this sets us up for a disjunctive syllogism on lines 3 and 5, proving tilde L, which was our goal. So now we've proven the consequent of the conditional in the conclusion. What's the last step of the proof? We can exit out of the scope of our original assumption and create this new conditional with our assumption on line 1 as the antecedent and the implication we derived from it on line 6 as our consequent.